Welcome to the deep dive. Today we're talking about a specific sequence from the Online Encyclopedia of Integer Sequences, the OEIS.
That's right.
And for those maybe following the OEIS podcast, perhaps number theory students interested in how these sequences appear everywhere, this one is A000241. It tracks something called the crossing number of the complete graph with n nodes. We usually write that as Kn.
Yes, K-A-N. And this sequence, A000241, it's really a fascinating case study. It looks simple, just a list of numbers, but it represents a combinatorial question that's led to some, well, pretty deep and persistent mathematical challenges.
It touches on graph theory, geometry, even computation, right?
Exactly. It connects quite a few areas.
Okay. And to help us unpack this, we've got a few different sources we'll be drawing on. We've got bits from a paper, I think from Toyota Technological Institute at Chicago, looking at algorithms for crossing numbers.
Yes, some recent work there.
Parts of a graph drawing tutorial, more practical maybe.
Showing how people actually draw these things.
And then sections from a survey that looks at different kinds of graph crossing numbers.
A broader overview of the different variants, yes.
So our mission today is, well, to use these sources to figure out what exactly is this crossing number, especially for these complete graphs, K-A-E-N. Why is finding it so tough?
And what are some of the ways researchers are trying to tackle it?
Yeah.
It's really a fundamental concept, so this should be a good introduction seen through this one OEIS sequence.
Okay, basics first then. The crossing number, what do the sources say it is?
So the standard definition, the one we usually mean when we say the crossing number, CRG, is the smallest possible number of crossings you can get when you draw a graph G on a flat plane.
Crossings meaning where edges intersect.
Exactly, where the two edges cross over each other, but not at a vertex where they're supposed to meet. Just, mid-air intersections in the drawing.
Okay, so you're trying to find the layout, the drawing, that has the absolute fewest of those overlaps.
Precisely. It's the minimum number across all possible ways you could draw it. And this number, CRG, it tells you something about how, let's say, non-planar the graph is.
Non-planar, meaning it can't be drawn flat without crossings.
Right. If CRG equals 0, then the graph is planar. You found a way to draw it perfectly flat, no edges crossing except at their endpoints, the vertices.
Like a simple square graph, maybe? K4?
Exactly. K1, K2, K3, K4. These are all planar. You can connect every pair of nodes in those graphs without any edges crossing. Their crossing number is 0.
But our sequence, A000241, is specifically for Kn, the complete graph.
Yes, Kn, where you have n vertices and every single pair of distinct vertices has an edge connecting them.
So they get really dense really quickly.
Incredibly dense. The number of edges shoots up quadratically as n increases.
And A000241 lists the minimum crossings for K1, K2, K3, and so on.
That's the sequence. 0, 0, 0, 0, 0, then it starts climbing.
The sources mention this has a history, right? Something about Turan's brick factory.
Yes. Turan's problem from the 1940s. It's often cited as an early motivation. He was thinking about, well, laying out railway tracks between kilns and storage depots at a brick factory and wanted to minimize the number of places tracks crossed.
Sounds very practical.
It was a very concrete problem that led to this more abstract graph theory question. Then researchers like Harary and Hill formalized the idea of a crossing number for any graph in the 50s and 60s.
And figuring out the number for KNN and also for KNS, the complete bipartite graphs, was a big focus early on.
Yes. People like Guy, Hill, Rogers, even Urges were deeply involved in trying to determine these values.
So with all that history and brain power, you'd think we'd have a formula for KNN by now.
You would think so. But this is where A000241 gets really interesting and, frankly, quite surprising. It turns out that finding the exact value of CRENN, even for not-so-large values of n, is remarkably difficult.
How difficult? What do we actually know?
Well, our survey source points out that the exact values, they're currently known only up to n equals 27.
27, that's it.
And interestingly, also for n equals 30. But for everything else above 27, apart from 30, we only have bounds, not the exact number.
Wow. That's much lower than I would have guessed. Why is it so hard to just calculate it?
It boils down to the definition. Finding the minimum over all possible drawings, the number of ways you can arrange endpoints in a plane and draw the edges between them, it's astronomically huge.
The combinatorial possibilities just explode.
Exactly. How do you prove that a particular drawing, maybe one you found with, say, 100 crossings, is truly the best possible? That no other arrangement, no matter how clever, could achieve 99 crossings?
You'd have to rule out everything else.
Essentially, yes. Or have a very clever proof technique. For small n, you can sometimes manage it, often with computer assistance now. But as n grows, exhaustively checking becomes impossible, and finding those proofs is a major mathematical challenge.
So the sequence A000241 starts 0000, then K5 is 1, K6 is 3, K7 is 9, K8 is 18. Those early ones are sorted.
Yes, those were figured out quite a while ago.
But getting the number for, say, K31, currently unknown?
Currently unknown. We have good estimates, lower bounds and upper bounds, that squeeze the possible value into a range, but the exact integer isn't pinned down.
That really highlights the difficulty. Now, the sources also bring up a variation, the rectilinear crossing number, CRR.
Yes, Courant of G, often written that way. It's similar, but with one really important extra rule. All the edges must be drawn as straight line segments.
No curvy lines allowed.
No curves. You place your n vertices as points in the plane, then connect every required pair with a straight line. The rectilinear crossing number is the minimum number of intersections you get across all possible ways of placing those endpoints.
So you can choose where the points go, but the lines are then fixed as straight.
Correct. You lose the freedom to bend edges around each other.
Does that restriction, does it change the minimum number of crossings you can achieve?
It absolutely can, and sometimes in a way that feels a bit backwards at first.
How so?
Well, the sources give the example of K8, the complete graph on 8 vertices. The standard crossing number, CRK8, where you can use curves, is 18.
Okay, 18.
But the rectilinear crossing number, K-bar, K8, where you must use straight lines, is 19.
19. It's higher when you force straight lines.
Yes. It means that the absolute best way to draw K8 with minimum crossings requires using at least some curved edges to avoid an intersection that you're forced into if you stick strictly to straight lines.
Huh. That's really not obvious. You'd almost think straight lines would be simpler, maybe less prone to crossing.
It shows that the optimal geometric arrangement is different depending on whether you allow curves or not. The flexibility of curves can sometimes let you untangle things more effectively.
That difference itself seems mathematically interesting.
It is.
Yeah.
And there's another fascinating connection mentioned in the sources related to this rectilinear number. If you look at the limit of K-bar, Kn, divided by and choose 4.
Okay, the number of ways to pick 4 vertices.
Right. As n gets very large, that ratio approaches a constant. It's called the rectilinear crossing constant. And remarkably, this constant is related to Sylvester's 4-point problem.
Sylvester's problem? Isn't that about picking 4 random points and the probability they form a convex shape? From geometric probability?
That's the one. A classic 19th century problem. The fact that its solution connects to the limiting behavior of how many times straight lines cross in a complete graph.
Yeah.
Well, it's one of those beautiful, unexpected links between different mathematical worlds.
Graph theory and geometric probability meeting via the sequence. Okay, so calculating these crossing numbers, whether standard or rectilinear, is clearly hard work, especially for AN.
Extremely hard.
Which probably means the general problem for any arbitrary graph is tough computationally.
Absolutely. The sources confirm what's well known in the field. Computing the standard crossing number CRG for a general graph G is NP-complete.
NP-complete, the class of problems where we basically don't expect to find an efficient algorithm that guarantees the exact best answer for all inputs, especially large ones.
That's the implication. Finding that minimum number is, in the worst case, likely to require an amount of computation time that grows exponentially with the size of the graph.
So, intractable for large, complex graphs in practice.
For finding the exact minimum, yes. But that doesn't mean people stop working on it. The paper from the Toyota Group, for instance, focuses on algorithms.
Right. They mentioned an efficient randomized algorithm.
Yes, one that gives an approximation to the minimum crossing number. It doesn't promise the exact minimum, but it gets you a drawing with a number of crossings provably close to it. And their work significantly improved how close that approximation is compared to previous algorithms for general graphs.
Which is often good enough for practical uses, right? Getting close to optimal.
Often, yes. If you can reduce crossings significantly, even if not to the absolute theoretical minimum, that's a huge win for visualization or chip design.
And are there specific types of graphs where it's easier?
Oh, definitely. The sources mention this too. The most basic case is planarity testing, checking if CRG is 0. That can be done very efficiently. Linear time, basically as fast as reading the graph description.
Using standard algorithms like depth-first search?
Exactly, or related techniques like PQ trees. And beyond planarity, for certain classes of graphs, like graphs that are almost planar, CAPEX graphs, or graphs that can be drawn on simpler surfaces bounded genus, there are better algorithms, sometimes even polynomial time exact algorithms or much better approximations.
So the structure of the graph really matters for complexity.
Very much so.
Now, thinking more broadly about drawing graphs, not just minimizing crossings, the sources mention other techniques, like force-directed layouts.
Yes, the graph drawing tutorial and the survey touch on the wider field. Minimizing crossings is one important goal, but not the only one. Sometimes you want to minimize the number of bends and edges, especially in things like circuit diagrams or orthogonal drawings.
Like making the wires take fewer turns.
Precisely. Network flow algorithms can sometimes be used for that. And then there are force-directed methods. These are very popular for general visualization.
How do they work?
You sort of simulate physics. Imagine nodes pushing each other away like magnets repelling, while edges act like springs, pulling connected nodes together. You let the system settle into a low-energy state.
And that naturally tends to produce a nice layout.
Often, yes. It tends to spread nodes out, keep connected nodes reasonably close, and minimize edge lengths.
Yeah.
While it doesn't explicitly target crossing minimization, the layouts often have relatively few crossings just because things are spread out nicely. It's a heuristic approach, very useful for making sense of complex networks visually.
Okay, let's pull back to the big picture. We've dived into OEIS A000241, this sequence for KNT. Why does understanding all this about crossing numbers actually matter?
Well, we've touched on some reasons. For graph drawing and data visualization, it's fundamental. If you're drawing a complex network social interactions, protein pathways, internet structure, minimizing crossings makes the drawing much easier to read and understand.
Reduces the visual spaghetti.
Exactly.
Yeah.
Less clutter, clearer relationships. Then there's the very practical engineering side, like VLSI design.
Chip layouts.
Right. Every time wires have to cross on a chip, it usually requires adding another layer. Using vias, it takes up space, can cause interference. Minimizing those crossings is a direct factor in making chips smaller, faster, cheaper to produce.
So it goes from abstract math right down to the hardware.
It really does. And theoretically, studying crossing numbers pushes the boundaries of combinatorics, algorithm design, and computational complexity. Understanding why this seemingly simple property is so hard to compute tells us about the limits of computation itself.
So this deep dive into A000241, it really opens up a lot. You start with a sequence of integers, and you end up discussing combinatorial geometry, NP-completeness, chip design. It's a great illustration, especially for number theory students, of how sequences can encode really deep mathematical problems.
Absolutely. It's a classic example of a problem that's easy to draw this graph with the fewest crossings, but incredibly difficult to solve completely. It shows that simplicity in formulation doesn't mean simplicity in solution.
Okay, so we've journeyed through OEIS A000241, the crossing number for complete graphs, KINN. We've seen, using our sources, that it represents this fundamental but surprisingly hard graph theory problem.
With exact values known only for relatively small n, highlighting the computational challenge.
And we saw those interesting connections, like the difference between standard and rectilinear crossings, and that link to Sylvester's problem in geometry.
Despite the general problem being NP-complete, research is very active, finding better approximations, tackling special cases, and using diverse graph drawing techniques.
So here's a final thought to leave you with. We've seen how hard it is to find the absolute minimum crossings for even a simple, highly structured graph like KNN. Given that, what does it suggest about our ability to truly, perfectly optimize the layouts of the much more complex, irregular, massive graphs that model real-world networks and systems? Are we always going to be dealing with good enough rather than perfectly optimal when it comes to visualizing and designing complex interconnected systems?